Even, pick any positive integer. If it's even, divide it by 2. If it's odd, multiply by 3 and add 1. Repeat. The conjecture, sitting unsolved for nearly 80 years, says you will always, eventually, land on 1. Always. Every single number. And a new paper published in May 2025 by mathematician Shaimah Saeed Sultan claims to have built a structural framework that proves exactly that. Today on Copilot Podcast, we're breaking down the Collatz conjecture, specifically what this new squeeze-drift-residue framework actually argues, why the three-part structure it builds is so mathematically powerful, and what it would mean if this holds up. I've got someone here who has gone deep into this paper, and I want to start with the most basic question possible. Why has this problem been so hard for so long?
So the brutal thing about the Collatz conjecture is that it looks like a game you'd play on a napkin. The rule is genuinely that simple. Odd numbers go up via 3x plus 1, even numbers come down via division by 2. And yet the behavior of the trajectories is so chaotic, so unpredictable, that mathematicians have essentially had no structural handle on it for decades. J.C. Lagarius, who is probably the world's leading authority on this problem, wrote in 1985 that the conjecture resists all standard mathematical approaches. And Terence Dow, Fields Medal winner, one of the greatest living mathematicians, published a major result in 2019 showing that almost all orbits attain almost bounded values, which is progress, but it's still not a proof.
So even Tau couldn't crack it fully.
Right, and that tells you something about the difficulty level here. What makes it so slippery is that the map mixes multiplicative and additive operations in a way that doesn't fit neatly into any one branch of mathematics. It's not purely number theory, it's not purely dynamical systems, it's not purely combinatorics. It touches all of them and sits comfortably in none.
Okay, so let's actually set the stage properly. The paper is specifically about ruling out what it calls non-trivial cycles. Can you explain what that means and why that's the central question?
Yeah, so the Collatz conjecture has two parts to it, really. One is whether any trajectory could go off to infinity, just keep growing forever and never come down. The other is whether there could be a cycle, meaning a sequence of numbers that loops back to itself without ever hitting one. We already know one cycle exists. It's the trivial cycle, which is just 1, 2, 4. You hit 1, multiply by 3 and add 1 to get 4, divide by 2 to get 2, divide by 2 again to get 1, and you're back. That's the only cycle we want. A non-trivial cycle would be some other loop, some set of numbers that just circulate among themselves forever, never reaching one. This paper's central claim is that no such loop can exist.
And the way it rules that out is through this three-part framework: squeeze, drift, and residue. Before we get into each one, can you give me the 30-second version of what the overall argument is?
The 30-second version is this. The paper shows that any hypothetical non-trivial cycle would need to satisfy three conditions simultaneously. It would need to satisfy the squeeze condition, the drift condition, and the residue condition. And the argument is that these three conditions are mutually incompatible. They form a closed contradiction. Satisfying one forces you to violate another. So no non-trivial cycle can exist because it can't pass all three tests at once.
Okay, I want to dig into each of those. Let's start with squeeze because that's the foundation. What is the squeeze inequality?
So the paper analyzes the Collatz map by looking at what it calls odd-to-odd blocks. Instead of tracking every single step, you zoom out and look at the journey from one odd number to the next odd number. Each of those journeys consists of some number of odd steps, call that L, and some number of even steps, call that R. The squeeze inequality says that for any block where the odd value doesn't grow, you need R to be greater than L times log base 2 of 3. And since log base 2 of 3 is approximately 1.585, that means you need significantly more even steps than odd steps. Every odd step has to be followed by at least 2 even steps on average.
So the even steps are doing more work than the odd steps.
Exactly, and that's the key insight. The odd step multiplies by roughly 3, which is an expansion. The even steps divide by 2 repeatedly, which is a contraction. The squeeze inequality is saying that the contraction always wins. The even steps always dominate the odd steps in any admissible block. The paper calls this even step dominance, and it means every valid block is inherently dissipative. It shrinks things. It can't sustain growth.
And this is where the paper introduces the block transform, right? That formula K of x equals 3 to the L times x plus c, all divided by 2 to the R? Yes, exactly. The block transform is the algebraic encoding of the entire odd-to-odd journey. The 3 to the L captures the multiplicative effect of all the odd steps, the 2 to the R captures the divisive effect of all the even steps, and C is a correction term that depends entirely on the parity pattern, the specific sequence of odd and even steps in the block. What's elegant about this is that the squeeze condition, R greater than L log 2, 3, immediately implies that 3 to the L divided by 2 to the R is less than 1. So the block transform is a strict affine contraction. It always maps x to something smaller.
Okay, so squeeze establishes that every block shrinks. Now what's drift? Drift is what happens when you take logarithms of the block transform. Instead of thinking about the numbers themselves, you think about their logarithms, their sizes on a logarithmic scale. The drift function d of x measures the logarithmic change from one odd iterate to the next. It's defined as log base 2 of the ratio of the next odd value to the current odd value. And the key result is that under the squeeze condition, the drift is always strictly negative. The logarithm of the odd values is always going down.
So it's like a random walk that's always tilted downhill.
That's actually the exact geometric picture the paper uses. In logarithmic space, the Collatz dynamics look like a walk on the real line, where every step has a negative average. And the paper proves this rigorously. The cumulative drift over any block is L times log 23 minus R plus a small correction term epsilon. The squeeze condition forces L log 23 minus R to be negative, and the correction term is always too small to compensate. Even in the most extreme edge case, which the paper identifies as the pattern OEE, one odd step followed by exactly two even steps, the drift is still negative for all non-trivial inputs.
Wait, they actually check the edge cases? Like they go through every possible pattern?
They do, and there's a whole appendix on it. Appendix I classifies all valid parity patterns up to length 6. And what they find is striking. For lengths 3, 4, and 5, the only admissible patterns are ones with exactly one odd step. The first time you get admissible patterns with 2 odd steps is at length 6, and even then, the squeeze condition forces those patterns to have 4 even steps total. The even steps always dominate. It's a very concrete demonstration of what the squeeze inequality means in practice.
That's a really nice way to make it tangible. Okay, so squeeze gives you contraction, drift gives you the logarithmic descent. Now what's residue, and why do you need a third condition?
So residue evolution is the most subtle of the three, and it's what closes the argument. The residue map captures the fractional behavior of the odd-to-odd transitions. For each odd number x, you compute the ratio of the next odd iterate to x, and then you take the fractional part of that, the part after the decimal point, essentially. This lives in the unit interval from 0 to 1, and you can think of it as the phase of the trajectory on a circle.
Okay, so it's tracking something like the rotational position of the trajectory.
Exactly. And for a non-trivial cycle to exist, these residues would have to be periodic. They'd have to return to their starting configuration after going around the cycle. But the paper shows that under the squeeze condition, the residues drift monotonically in one direction. They don't oscillate, they don't return, they just keep moving. And a monotone drift on a circle can never close into a periodic orbit. So the residue condition independently rules out cycles, and it does so from a completely different angle than the drift condition.
So you have 3 independent obstructions, each one sufficient on its own, and they all reinforce each other. That's the power of the unified framework. The paper's central theorem states the implication chain explicitly. Squeeze implies negative drift implies mononone residue evolution, and mononone residue evolution implies no non-trivial cycles. Each arrow is strict and unavoidable. A non-trivial cycle would need to be a fixed point of the affine contraction, have 0 cumulative drift, and have periodic residue evolution. And all 3 of those requirements fail simultaneously. I want to pause on something here because I think this is where it gets really interesting. The paper doesn't just say cycles are impossible, it goes further and says every trajectory must converge to 1. How does it get from ruling out cycles to proving convergence?
Right, so this is the second major result, and it builds on the first. The argument goes like this. Negative drift forces the odd values to decrease indefinitely. They can't stay bounded on a non-trivial residue class because residue monotonicity prevents that. So the fractional part of log base 2 of the odd iterates must eventually approach 0. And when that fractional part vanishes, the trajectory is at a power of 2.
And powers of 2 just collapse straight to 1.
Deterministically, 2 to the k goes to 2 to the k minus 1, then 2 to the k minus 2, all the way down to 2, then 1. There's no branching, no choice, no chaos. Once you hit a power of 2, you're done. So the full implication chain the paper establishes is squeeze implies negative drift implies residue collapse implies you inevitably hit a power of 2, and hitting a power of 2 forces convergence to 1.
That's a beautiful chain. And there's this geometric picture the paper paints that I think really helps make it intuitive. Can you walk through that?
Yeah, the geometric interpretation is one of my favorite parts of the paper. It says you can think of the Collatz dynamics as acting simultaneously in 3 different spaces. On the real line, the block transform is a contracting affine map. It always pulls things toward a fixed point, but the fixed point is trivial. In logarithmic space, the dynamics look like a random walk with a persistent downward slope, negative drift. And on the unit circle, the residue map acts like a rotation with a monotone drift. It never closes into a loop. A non-trivial cycle would require a fixed point in all three spaces simultaneously, and the squeeze drift residue framework shows that's impossible.
3 spaces, 3 obstructions, 1 unified contradiction. I also want to talk about the two-adic tree structure because the paper spends a lot of time on it, and I think it gives a really different perspective on why this works.
So the two-adic tree is a way of organizing all the integers by their relationship to powers of 2. Every integer can be written as 2 to the L times m, where m is odd, and L is the two-adic valuation, basically how many times 2 divides the number. The paper shows that every odd integer m generates a branch of the form m, 2m, 4m, 8m, and so on. And the Kalatz map, when it hits an odd number, applies the 3x plus 1 step and then strips away all the powers of 2 until it reaches the next odd number. So it's constantly moving between these branches.
And the key insight is that every branch is just a scaled copy of the branch rooted at 1.
Exactly. Every odd branch is m times the set 1, 2, 4, 8, 16, which is just the branch rooted at 1, scaled by m. And the Kalatz map repeatedly strips away the scaling factor through division by 2, so every trajectory is being funneled toward the one branch. The paper calls this the two-adic funnel, and it's a really vivid way to see why convergence is structurally forced. No odd number can escape its branch indefinitely. The even steps keep collapsing the two-adic depth.
There's also this local structure the paper calls EOE, even, odd, even, that I found really elegant. What's that about?
So the EOE block is the local pattern around every odd integer m. The unique even predecessor of m is 2m, because the Kalatz map sends 2m to m by halving. The odd node is m itself, and the unique even successor is 3m plus 1, because that's what the odd step produces. So every odd integer sits in this rigid local structure. 2m goes to m goes to 3m plus 1. The paper proves this is invariant. It doesn't matter how you draw the Kalatz graph or how you order the odd roots. This local block is always the same, and it's the fundamental generator of the residue propagation dynamics.
So the local structure is rigid, even though the global behavior looks chaotic.
That's a really good way to put it. The chaos is in the global trajectories, which numbers you visit, in what order, how long it takes. But the local rule is completely deterministic and rigid. And the paper's argument is essentially that this rigid local structure, when you aggregate it through the squeeze drift residue framework, forces the global behavior to be convergent, even though it looks chaotic.
I want to bring up something that I think is worth acknowledging. This paper is making a very strong claim. It's saying the Kalatz conjecture holds, but the mathematical community has seen claimed proofs of famous problems before that turned out to have gaps. How should we think about this paper?
That's the right question to ask, and I think intellectual honesty requires sitting with it. The paper presents a coherent and internally consistent framework. The 3-part structure is well motivated, the arguments are detailed, and there are extensive appendices with computational verification. But a claimed proof of the Kalatz conjecture is an extraordinary claim, and it requires extraordinary scrutiny. The mathematical community would need to carefully verify every step, particularly the claims about residue monotonicity and the correction term epsilon being too small to compensate the negative drift.
And the paper itself is actually pretty transparent about what remains open.
Very much so. There's a whole section on open problems and future directions. The paper acknowledges that the distribution of two-adic valuations, how often V2 of 3x plus 1 attains large values, is not fully characterized. The combinatorial structure of valid parity patterns is described as largely unexplored. And the geometry of the residue map, whether it admits invariant measures, what its entropy is, those are listed as open questions. So the authors are not claiming to have resolved everything, just the central cycle question.
There's also something kind of fascinating in the acknowledgements section. The paper credits Microsoft's Copilot for helping with algebraic verification and structural exploration. That's a pretty notable thing to see in a mathematics paper.
It really is, and I think it's a sign of where mathematical research is heading. The acknowledgement is careful to say that all mathematical ideas, arguments, conceptual framework, and interpretations remain solely the responsibility of the author. But using AI as a tool for verification and exploration, that's a genuinely new development in how mathematics gets done. It raises interesting questions about what the role of AI in formal proof verification might look like going forward.
And speaking of the history here, the Collatz conjecture has this reputation for being almost dangerous to work on. Like, mathematicians have warned each other away from it.
Paul Erdős, one of the most prolific mathematicians of the 20th century, said that mathematics is not yet ready for such problems. And Lagarius, in his 1985 paper in the American Mathematical Monthly, documented how the problem had already consumed enormous amounts of mathematical effort without yielding to standard techniques. There's a real sense in the community that the Collatz conjecture sits at the boundary of what current mathematics can handle, which is part of what makes a structural framework like this one so interesting, even if it requires further verification.
So when you step back from all of this, the squeeze, the drift, the residue, the two-adic tree, the EOE blocks, what's the core insight that ties it all together? The core insight is that the Collatz map is not as chaotic as it looks. Underneath the apparent randomness of the trajectories, there is a rigid structural bias toward contraction. Every admissible block shrinks. Every logarithmic step goes downward. Every residue drifts mononically. The map is not a random walk, it's a biased walk, and the bias is always in the same direction. The squeeze-drift-residue framework is a way of making that bias precise and showing that it's strong enough to rule out any alternative long-term behavior.
And the practical consequence is that every number, no matter how large, is already on a path toward one. It just might take a very long time to get there. Right. And the paper makes this concrete through the two-adic funnel picture. Every odd number m sits on a branch that is just a scaled copy of the powers of 2 branch. The Collatz map keeps stripping away the scaling factor. Eventually, the odd component disappears and you're left with a pure power of 2. And from there, the descent to 1 is completely deterministic. No more choices, no more branching, just halving all the way down.
Here's what this really comes down to, I think. We started with a problem that looks trivially simple. Pick a number, follow 2 rules, end up at 1. And what this paper is arguing is that the reason you always end up at 1 is not a coincidence or a computational observation. It's a structural inevitability baked into the arithmetic of the map itself.
That's exactly it. And I think that's what makes this framework genuinely interesting, regardless of whether every detail of the proof holds up under scrutiny. The idea that you can decompose the Collatz dynamics into 3 interacting structural components, each one a different lens on the same underlying phenomenon, and show that they collectively form an impenetrable obstruction to non-trivial cycles, that's a conceptual advance, even if the technical details need refinement.
And the open problems the paper raises are themselves fascinating. The question of whether the residue map admits invariant measures, whether the framework generalizes to other Collatz-type maps of the form AXX plus B divided by 2 to the valuation, those are rich directions.
The generalization question is particularly interesting. The paper explicitly asks, for which pairs A and B does a squeeze-drift residue framework exist? Can the unified contradiction be extended to broader families of maps? That's pointing toward a deeper theory of arithmetic dynamical systems that goes well beyond the classical Collatz problem. So even if you're skeptical about the main claim, the framework opens up a landscape of new questions.
So here's my takeaway from all of this. We have a problem that's been open since the 1930s, that has resisted every standard mathematical techniques, that Erdős said mathematics wasn't ready for. And now there's a paper arguing that the reason it's true is not mysterious at all. It's 3 interlocking structural constraints that make any alternative behavior literally impossible. Whether this proof stands or needs refinement, the framework itself is a new way of seeing the problem.
And that matters independently of the proof status. In mathematics, a new framework that reframes a hard problem, even if it doesn't immediately resolve it, can be the thing that eventually leads to a resolution. The squeeze-drift residue lens gives future researchers a new set of tools and a new vocabulary for thinking about Collatz dynamics.
We started this episode with the simplest possible rule. Pick a number, follow 2 steps, end up at 1. And what we found is that underneath that simplicity is a 3-dimensional structural argument involving affine contractions, logarithmic walks, and rotations on the unit circle. The simplest problem turns out to have some of the deepest structure. That's the thing that's going to stick with me. Thanks for listening to Copilot Podcasts, and the next time you're stuck on something that looks simple but won't yield, maybe the answer is that you need 3 different lenses, not 1.